Hey everybody, tonight we're given an equation with two unknowns. Okay, so there's an infinite number of solutions to any equation where you have more unknowns um, than equations, and that's the case here. But we have some helpful stuff from number theory here that's going to uh, get us through this. Now, the main result here that's going to get us started is noting this fact right here about it's a divisibility test for 11. Okay, so if you take a look at this congruence, this is true modulo 11. And it's very easy to verify for n equals 1, right? For n equals 1, we just have 10 minus 1 is 11, right? But properties of congruences means it also holds as you raise. This is like an equality, and you can elevate it to powers and obtain a true statement. So what we can do is do a divisibility test. Notice that 2 is not a divisor of this. The sum of the digits is not divisible by 3, so 3 is not a divisor, 5 is not a divisor. It's a little harder to show that 7 is not a divisor, but let's check out 11. Okay, now there's an alternating test, and what you do is you just add up these digits, but you alternate the sign. And you alternate the sign precisely because of this statement. If you think about this, there's powers of 10 associated with each of these digits. For example, this would be 10 to the 4th, 10 cubed, 10 squared, and 10, right? So you see how the sign is going to alternate. So that's why you have 1. Here's a 10 to the 4th associated with this, 10 cubed associated with this, but minus 1 cubed is this minus sign you see here. So this statement right here is why this alternating test works. So oops, that should be a 2 right there, my bad. Okay, so let's write 2 here. Okay, and then you alternate your signs, plus 8, minus 8, plus 1. And you'll notice this sums to 0. This sums to 0. And this sounds kind of trivial, but 11 is a divisor of 0. Any number is a multiple. 0 is a multiple of any number is another way of putting it. Now here it's very useful that 11 divides 0. A lot of times this test is going to add up to some multiple of 11 where it makes more sense, okay? And that's the general, if you add this up and you get some multiple of 11, then that means this number has to be divisible by 11. But 0 is the trivial multiple of everything, right? So let's take advantage of that, folks. Now, if you do a division right here, you'll find out that this constant term, this 5-digit constant term, is equal to 11 times 1171. Now there's some work involved with this. You have to do that by hand, and it's rather tedious. You can make mistakes, but this is if you do a long division right here, divide 11 into this, you get 11 times 1171. And really, this is most of the work in the problem. Watch how this goes. Okay, so what we can do right here is take advantage of this difference of 2 cubes result, and we'll go ahead and since we have, I think 1171 is prime, even though I'm not sure it makes any difference here. So we can set a minus b equals to 11, right? Factors have to go somewhere, right? So we'll set a minus b equals to 11. Okay, now, so you see, this all is just, most of the work's already been done. I want you to sit and watch me do this. But I replaced a minus b with 11. Then we do this difference of 2 cubes result, very well-known result here. And then you can see what happened right here. What do we have here? A minus b, so this would be, a minus b is equal to 11, so we replaced it. But also a is equal to b plus 11, right? Okay. You see, that's exactly what we did right here, folks. This a squared got replaced with b plus 11 squared. AB got replaced with b plus 11 times b, just based on this assignment, based on the prime factorization. Okay, and the rest of this is just a lot of work. You can verify, you can check it out if you want to. We get to this point right here when we collect like terms. Now, this is what a minus b cubed is equal to. Remember, a cubed minus b cubed is equal to this expression, but remember, a cubed minus b cubed has a constant on the right-hand side, 12,881, and that's what happened right here, okay? Now, when you divide through by 11, you get this 1171. Again, this is, some work was required up here to do this by hand, no doubt about it, all right? So now, another thing to notice right here is, what do we have here? We factored the 3 out. We subtracted 1171 from 121 to get this constant, 1050 minus 1050. But notice 1050 is divisible by 3 because the sum of the digits, 5 plus 1, is divisible by 3, right? So that means we can, with impunity, factor a 3 out of this. Okay, so we'll have 3 times b squared plus 11b. Now, again, these divisibility tests really mean a lot because you wouldn't know necessarily that 3 was a divisor there. But again, if you add up these digits, you get 6. And 6 is divisible by 3, so the entire number is divisible by 3. And that's the very same thing. 10 is congruent to 1 mod 3, just like the 11 test, okay? Now, the constant here, it happens to be minus 350. Equals to 0. Now, y'all notice 350 here. We can drop the 3, but let's just go ahead and, what is 350? 350 is 7 times 50, right? 350 is 7 times 50, but if we steal a 2 away from 50, we get that 350 is 14 times 25. And those are the magic numbers in this, for this particular problem. Again, steal a 2 away, and you get, this is equal to 14 times 25. Why is that important? Because 25 minus 14 is 11, right? So you see, that's all this. This is a very arithmetic problem. What we get right here is we can divide through by 3, then factor this, folks, and we'll end up with b plus 25. Okay, the linear factor b plus 25 times the linear factor b minus 14. Right? And again, ladies and gentlemen, what I did is I divided by 3 first of all, and then I factored. All right, 0 divided by 3 is 0. That's the free lunch you get in this problem. Okay, and so what happens here is you get what b is equal to negative 25. Right, now remember, what was our substitution? Our substitution up here was a is equal to b plus 11, right? So we would have to add 11 to this to give a equals to minus 14. And sorry, it's hard to keep everything on the same screen, but that just goes all the way back to the fact that because of this factorization here, we equated this a minus b factor in the difference of 2 cubes to the smaller number 11, all right, and that leads to a is equal to b plus 11. Now so we have a pair of solutions. Now also for b equals to, what do we got? B is equal to 14. So that would imply from our previous, just like in the previous case, a is equal to 25. Okay, a equals 25 right here. So folks, the two solutions, I'll see if I can remember these, 25 and 14. So one solution would be 25 comma 14. Remember, we're looking for the Cartesian product solutions. Cartesian product of the integers is just ordered pairs that contain integers as coordinates. Okay, so this would be one solution. A would be 25, B would be 14. This is a member of the Cartesian product of the integers, and then flip this around. Notice the bigger number goes first. Just the order does matter here. Minus 14 is a bigger number than minus 25. Now their absolute values are 25 is bigger, but minus 14 is a larger number than minus 25 if you just think of the number line. So these are the two solutions, the two integer solutions. I want to stress that an equation like this does have an infinite number of solutions. You could pick any pair of numbers you wanted to that had a difference of 12, 8, 81, then cube root each one of those and substitute in here, and that's a solution, right? But you were given up front that there are integer solutions, and these are the only two integer solutions owing to the unique factorization of this difference of two cubes result. Anyway, I hope you enjoyed that. I liked it. Prime factorization and then the difference of two cubes algebra is what helped us escape with a solution here. Thanks for viewing.